A genuine collat cycle only exists if it satisfies a strict integer condition within the accelerated odds Syracuse map. We can map the exact boundaries of that condition before calculating a single trajectory. For any sequence of operations, what we call an exponent word, w, we can define a divisor, d of w. This is 2 to the power of the two-adic valuation, k, minus 3 to the power of the word length. We pair this with the exact Syracuse constant for that sequence, c of w, to form the affine cycle equation. For a valid positive integer cycle to exist, the divisor must perfectly divide the Syracuse constant. If d of w divides c of w, a cycle is mathematically permitted. We represent the steps of this theoretical cycle as a single Syracuse exponent word, w, tracking the sequence of operations from start to finish. But we can take this global sequence vector and fracture it into two distinct adjacent subsegments, u and v. If a global cycle exists across the entire word, we have to determine exactly what arithmetic constraints that global divisibility forces onto the local data of those two segments. These pieces do not operate in isolation. Their local arithmetic must be deeply entangled to allow the global sequence to close into a perfect loop. To characterize that entanglement, we have to execute a multi-scale closure test on the split word, w equals u concatenated with v. Mapping this subword compatibility establishes the arithmetic groundwork for understanding how local properties scale into global cycle structures. To see how these pieces interact, we map the structural engine of the Syracuse map, the affine transfer matrix. This matrix places the two-adic sum in the top left, the negative Syracuse constant in the top right, and the three-adic length in the bottom right. The affine map acts as an exact monoid homomorphism. Appending one sequence to another translates flawlessly to multiplying their respective matrices. The main diagonal elements simply multiply their respective bases, summing the exponents for the two-adic and three-adic values of the combined word. The complexity lies in the upper right quadrant. This entry calculates the negative Syracuse constant for the entire combined sequence. Extracting that entry gives us the exact concatenation law for the constant. In the first term, the components of the initial segment, u, shift by a factor of 3 raised to the length of the trailing segment, v. In the second term, that trailing segment scales by the two-adic sum of the initial segment. This concatenation law is an intrinsic algebraic reality of the map. It exists independent of any modulo restrictions we might impose when searching for cycles. By expressing the sequence logic as a matrix product, we secure the exact algebraic foundation needed to test for global cycle closure constraints. We can now execute the multi-scale closure test by enforcing the global divisor condition onto that concatenation law. The concatenated constant must equal 0 modulo the global divisor. Because we are working modulo 2 to the k of w minus 3 to the length of w, we can use a critical substitution. 2 to the k of w is congruent to 3 to the length of w. To align the exponents, we multiply the entire congruence equation by 2 to the power of k of v. The exponents of 2 combine to form 2 to the k of w, which immediately collapses into 3 to the length of w through our substitution. This creates a common factor. We can extract the invertible unit, 3 to the length of v, and cancel it out from the entire left side. The expression simplifies sharply, leaving the final cross-relation constraint. This equation proves that the individual subsegments do not need to satisfy the cycle condition locally within themselves. Instead, their normalized projections act as precise, cross-coupled arithmetic complements modulo the global divisor. A collat cycle cannot be viewed as a chain of locally valid segments. It is a globally entangled system where every single subword exists solely to mathematically cancel out its counterpart. Does this exact compatibility constraint hold if the word is shattered into infinite recursive subdivisions? If we partition the global word into an arbitrary sequence of subsegments, we translate this multiple subdivision back into the affine framework, expanding the original matrix into a vast cascade of matrix products. The absolute structural guarantee of persistence here is the associative property of matrix multiplication. Because matrix associativity is immutable, the global upper right matrix entry, representing the negative Syracuse constant, remains strictly invariant, regardless of how or where the sequence is sliced. The cross-relation constraint is therefore an intrinsic, persistent algebraic property of the state space, completely independent of the unsplit cycle equation. Local independence is prevented by the matrix structure. Global entanglement persists down to the smallest atomic subdivision. This persistence leads to a predictable limitation in fixed prime power sieving algorithms. Historically, researchers attempt to rule out cycles by identifying local obstructions, finding cases where a subword hits a maximal 2-adic or 3-adic valuation limit. The cross-coupled constraint exposes exactly the escape mechanism that breaks these sieves. Concatenation introduces new degrees of freedom, the relative coefficients 3 to the length of u and 2 to the k of v. These specific coefficients act as mathematical units modulo prime powers. They effectively swap the valuation weights of the subsegments. This swapping allows two subwords, even those capped at their own local maximum valuations, to completely cancel each other out at higher scales, reducing the entire expression to 0. This arithmetic cancellation mechanism renders any single-length structural obstruction inherently localized and blind to the broader scale dynamics. Global Collat cycles remain hidden behind this precise multi-scale entanglement. No local sieve can ever outscale the recursive cancellation permitted by the affine transfer matrix.